Welcome back, everybody. Today we're going to discuss the basic theory of Jacobians and the main theorem of elliptic curves. We'll need this theory going into Eichler-Shimura. So what is a Jacobian? Well, let's let K be an algebraically closed field. Let's let X be a non-singular algebraic curve defined over K. The Jacobian of X, written Jac of X, is an abelian K variety with the following universal property. It's equipped with a pointed map phi from X to Jac X, sending some base point X naught to E, the identity element of Jac X, because it's an abelian variety, so it has an identity element, such that every pointed morphism X naught to A comma E to an abelian K variety A from X factors through phi. So the picture is something like this. You've got this map X to Jac X, sending some point X naught to E. All right. If you take any other abelian variety A and take any other pointed morphism, sending X naught to the identity element, let's also call it E, I guess, of A, then there will be a unique morphism from Jac X to A commuting the triangle. Okay, you have to make sure Jac X actually exists. You can construct it in a couple different ways. One way is it's the moduli space of degree 0 line bundles on X, if you're familiar with line bundles. It's also the quotient of the dual space of the holomorphic 1 differentials on X mod the first integral homology group of X. So you can see Diamond and Sherman for these viewpoints. Okay, up next is the Picard group. So let's let X be as above, our curve. Let's let K of X denote the function field of X. Remember, a divisor on X is a finite formal sum of points weighted by integers. We'll call the points, well, we'll call the formal points parentheses P and their weights N sub P. Let's let div 0 of X be the group of degree 0 divisors on X, where we recall that the degree of a divisor D equals sum of NP parentheses P is just the sum of the coefficients NP. Okay, it's usually written deg D. Let's denote by div L of X the group of principal divisors on X, or a principal divisor, we recall, is just a divisor of the form div F for some F in the function field K of X. And div F, remember, is just the divisor recording the zeros and the poles of F. So a positive coefficient in front of a point indicates a 0 at that point of F to that order, and a negative coefficient in front of a point indicates a pole of that order for the function F. It's a basic fact from the theory of divisors that div L of X is a normal subgroup of div 0 of X. And so you can form the quotient group pic 0 of X, which is div 0 of X mod div L of X. This is called the degree 0 Picard group of X, or just the Picard group of X. Okay, and so then we have Obel's theorem, very important theorem here. It says let X be a complex, so now I'm working over C, a complex non-singular projective algebraic curve. Then there's an isomorphism of varieties from pic 0 of X to Jac of X. This shouldn't be too surprising, naively speaking, because, you know, moduli space of degree 0 line bundles, degree 0 divisors, presumably there's some matchup there. But yeah, this is an isomorphism of varieties. This is covered in Diamond Sherman chapter 6, although the information there is not complete. I have a set of notes on Diamond and Sherman that has more information and references on it. Those are available upon request if you would like them. But it also turns out that if X has genus G, it's a curve, so it's got some genus G, then Jac X is isomorphic to a complex G-dimensional torus. So in other words, it's isomorphic to something of the form C to the G mod L sub G for some lattice L sub G in C to the G. So C to the G here just means C cross C cross C, blah, 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 G times. Okay, and again, the references above here are going to contain the information you need for that. Okay, what happens if we apply this theory specifically to the case where X is an elliptic curve over the complex numbers? Well, if X is a curve with genus G bigger than 0, we've got our embedding from X into the Jacobian of X. That's the map I was talking about above. Here is the map. It sends a point little x and big X to the divisor class, or the coset of the divisor X minus X naught, where X naught is our base point in X from earlier. And these brackets just denote taking the coset. I'm using Obel's theorem here to think of this as pic 0, right? So this is div 0 mod div L. So what I'm saying is take the degree 0 divisor X minus X naught and look at its coset in this quotient group here. Okay, now when X is an elliptic curve, so when this genus is 1, this map here is an isomorphism of varieties. Okay, so if X is a complex elliptic curve, it's isomorphic to its own Jacobian, which shouldn't surprise you because diagram theoretically, the Jacobian of X is like, I don't know, in quotes, the smallest abelian variety containing X. But if X is an elliptic curve over C, it's already an abelian variety. So it should naively be its own Jacobian, and that turns out to be true. Okay, so again, Diamond and Sherman chapter 6 talks about this. Okay, one thing we should be aware of with Jacobians is if I give you a non-constant morphism H from X to Y of non-singular projective K curves, there are induced natural pullback and push forward maps of Jacobians. So there's a pullback map H star from the Jacobian of Y to the Jacobian of X. And there's also a push forward map H lower star from the Jacobian of X to the Jacobian of Y. One of these two is pretty easy to construct and the other one's not so easy. But again, Diamond and Sherman chapter 6 is your reference for that. Okay, so we'll need this probably next video even. And then finally, I'd like to just, mainly because it's cute, but also because its proof uses the theory of Jacobians, I'd like to give you the main theorem of elliptic curves. Although to be fair, I don't know why it's called the main theorem of elliptic curves. I don't even know if it's called that. I know I learned when I first learned this theorem, wherever it was, the first source I read this in, it was called the main theorem of elliptic curves. I have not been able to locate that source since. And I also have not seen any other source call this theorem the main theorem of elliptic curves. So anyway, I'm just going to call it the main theorem of elliptic curves. And the setup here is we know, elliptic curves over the complex numbers are one-dimensional complex abelian varieties, right? So the question is, like, if I give you an algebraically closed field of characteristic 0, are there any other one-dimensional abelian K varieties besides the elliptic curves over K? And the answer is no, according to the main theorem of elliptic curves. The main theorem says, let K be an algebraically closed field of characteristic 0, then the one-dimensional abelian K varieties are exactly the elliptic K curves. Okay, so for an introduction to the proof of this, you should look at Diamond Sherman chapter 6, but the information there isn't complete. I found this article online called Chen on one-dimensional group varieties. I think it's actually called on one-dimensional group variety. There's a typo in the title. And that has more of a full proof. And there are a variety of other sources, Milne's notes and all kinds of things like that. And again, the point of me bringing this up is it's obviously relevant as we're talking a lot about elliptic curves lately, but also the proof uses the theory of Jacobians. And so next time we'll look at Goose's theorem and we'll push towards Eichler-Shimura. And so thanks for watching and I'll see you then.